Like, I can do that longer than I can do push-ups.
All right. Good afternoon. Any question before we start? So we continue on failure theories for ductile material. So far, we covered maximum shear stress theory, which says the failure criteria says the failure occurs when tau max equals to Sy over 2, sigma 1 minus sigma 3 divided by 2 equals to Sy divided by 2, or sigma 1 minus sigma 3 equals to S1. Factor of safety is defined as Sy over 2 divided by tau max, or Sy divided by sigma 1 minus sigma 3. If you want to incorporate factor of safety, the maximum allowable shear stress is going to be Sy divided by 2 divided by N, and shear yield strength is defined as half of Sy, where Sy is the yield strength. Second theory that we covered yesterday was distortion energy theory. It defines the von Mises stress which can be defined by any of these four equations. They are the same depending on the type of the problem. You can use any of these equations. So if you are given with three principal normal stresses, you can find the von Mises by equation 512. If you have plane stress elements, one of the principal normal stresses would be 0. You have sigma A or sigma B, so you can use this. If you are given with the state of stress, you don't need to find principal normal stresses, just plug in the numbers here to find von Mises stress. And for plane stress elements, this equation is going to change to this. So in any case, you will find sigma prime or von Mises stress. Then compare this with the Sy, which is the yield strength. So this is the failure criteria. If you want to define factor of safety, is going to be Sy divided by sigma prime. If you want to incorporate factor of safety, the von Mises should be equal to Sy divided by N. So these are what we covered so far. If x-axis is representing sigma A and y-axis representing sigma B, for maximum shear stress theory, if I want to plot the failure criteria, meaning this one. It's gonna look like a square. So for maximum shear stress theory, it's gonna look like this. Oh, not here. These two are square, and here we are gonna have a line. Depending on which quadrant we are located in, sigma 1 and sigma 3 would be different. So we are gonna end up to this. Now, for distortion energy theory, if we have sigma A and sigma B, if I want to plot this, it's not a linear function, it's gonna look like something like this. The equation of one misses or failure theories for the distortion energy theory is gonna look like this. So any point inside this area is gonna be safe, and any point out of the area it's gonna be failure occurs. As you see, the distortion energy theory is less conservative than maximum shear stress theory. Just think about a point here, or one point there, or right here, somewhere between these two. Based on the distortion energy theory, we don't have any failure for this point, but based on the maximum shear stress theory, it's gonna see the failure because it's out of the safe zone. So same thing for here. It's inside the oval, but it's outside of the box. So this one is more conservative than this. So if you need to have more reliable design, you need to use maximum shear stress theory. For doing the analysis, if you are not asked which method should be used, you should use the distortion energy theory. What do I mean by analysis? If you are given with the mechanical component and you want to see if the failure occurs, you are going to use this to check that. You are not going to do design. You are going to just check doing the analysis. But if you want to do design and you were not asked which one should be used, it's better that we be more reliable and use maximum shear stress theory. So design, or I can say more conservative, or more reliable, less conservative, and more for analysis. Now, if I want to check or compare distortion energy theory with empirical results or real data, I'm looking at this figure 515. The dots that you will see, it's presenting the real data. These points representing the failure points. We tested and the failure occurs here. As you see, distortion energy theory, it's gonna be a better fit for experimental data than the maximum shear stress theory. So it has a better fit to the real data comparing to maximum shear stress theory. So this is one thing that we can say about that. But as I said, it's MSST, it's a better approach or better theory for more reliable design if it's design. Any questions so far? We did this in the class, yesterday class. SSY for MSST is SY divided by 2. Maximum shear stress theory, based on this theory, maximum shear stress theory is going to be 0.5 of SY, but based on distortion energy theory, SSY would be SY divided by S square root of 3 or 0.707 SY. 0.57, sorry. I think I wrote wrong number yesterday, so it's going to be 0.577 SY, not 0.7. So 1 over S square root of 3 is going to be 0.577 times SY. So based on this theory, the component can carry out the greater shear stress. So now let me work on one example before we move on. Brittle column theory. A hot roll steel has a yield strength of, for compression and for tensile, they are the same and are 100 kpsi. And a strain at the fracture point is 0.55. If this material is under the stress element of sigma x equals to 60 kpsi, sigma y 40 kpsi, and shear stress of xy equals to negative 15 kpsi. Find factor of safety based on maximum shear stress theory and distortion energy theory. So we have a mechanical component. It's made of steel with these mechanical properties. As you see, they, for compression and tensile, they have the same strength. So we can use these two theories. Otherwise, we cannot use these two. We have to use this here, DuctileMoher. Why we are given with this? Because we should check first if we have a ductile material or brittle. If you remember, if sigma epsilon f or S strain at the fracture point is greater than 0.05, we have ductile. If it's less than 0.05, we have brittle. If you have brittle, you cannot use these two. So since it's 0.55, we can make sure that it's a ductile material. So let me start with maximum shear stress theory. To apply the maximum shear stress theory to find the factor of safety, I should know the SY, which I know. I should find the sigma 1 and sigma 3. I'm given with the stress element. I know how to find sigma 1 and sigma 2. Sigma A and B would be sigma x plus sigma y divided by 2 plus and minus S square root of from stress transformation, we can find sigma A and sigma B. Sigma X is 60 plus 40 divided by 2 plus and minus square root of 60 minus 40 divided by 2 square plus tau xy is negative 15. If it's negative 15, it should go down. So the results would be 68 and the other one is 32. So the principal normal stresses for A and B is going to be 68 and 32. We have 68, 32, and the last one is 0. So the greatest is 68. The smallest, sigma 3, is 0. To find n, I divide sy, which is 100 kpsi by 68 minus 0 . I just changed everything to psi, but I know that both are in psi. I could cancel them out. So 100 divided by 68 is gonna be 1.47. Based on maximum shear system. Good. So before I calculate the factor of safety for distortion energy theory, do you think that I'm gonna get the number greater than 1.47 or smaller than? If I do the calculation for distortion energy theory, am I going to get a number greater than 1.47 or smaller than 1.47?
Small.
And for DET, it should be a greater than, and for maximum shear stress theory or less than. It's gonna be, we expect to get the greater value because this technique, this theory is less conservative than maximum shear stress theory. So the factor of safety for more conservative method should be less than the factor of safety for less conservative method, which is the distortion method. So let me do So for distortion energy theory, if I want to find n, I should find von Mises theory. I already could find sigma A and sigma B, so I can find the von Mises stress term by using equation 513. But if you just want to use sigma x equals to 60, sigma y equals to 40, and tau xy equals to negative 15, you can simply use this equation to find sigma prime. You will get the same result. I'm just saying, to save the calculation, you don't need to calculate sigma A and sigma B if it's not needed. But since I already needed sigma A and sigma B for MSST, I'm going to use that, so sigma prime is gonna be 68 squared minus 32 times 68 plus 32 square root is gonna be 59. The unit is, it's a S stress, it's a K PSI, whatever is the unit of this. So N for distortion energy theory would be Sy divided by sigma prime, which is 100 divided by 59, 1.6 versus 1.47. All right. Any question on this? So now let's move on. The last theory on brittle material, which is DuctileMoher theory. Some material some ductile materials have different SYC and SYT. For brittle material, it's usual, but some or a few ductile materials have this specification. If you have this type of the material, you cannot use these two. You should use DuctileMoher theory. But DuctileMoher theory can be applied for all ductile material, including these types. So let me first introduce the Mohr theory. Then DuctileMoher theory is going to be the simplified case of the Mohr theory. So let's see how this theory is going to work. Suppose for a specific material, you make the test specimen out of that material and you apply tensile force. By applying tensile force, you are gonna do test and you can find yield strength for tensile. So SYT can be obtained by this one. So for this test, if I want to draw the Mohr circle, I only have normal stresses. At the failure point, this stress is going to be equal to SYT. So if I want to locate that, it's going to be somewhere here and here. So the circle, if it's about the circle is going to look like this, SYT, for this case. Just imagine one point here, point A, point B. Point B is 0, 0, which is the origin. Point A is going to be SYT at 0, which is going to be that point, draw a circle. Now do the test for pure compressive load. So if you do that, the maximum yield strength is going to be SYC. If I draw the Mohr circle, it's going to be somewhere here, negative SYC. And this circle is going to look like this. Do one more time this test for pure shear stress. Apply torque. Apply torque and find the SSY or tau max. For this state of stress, if you plot that, it's gonna look like something like this. So shear tensile and compression. So this theory said if I has a bonding curve like this, something like this, through these three circles, the inside the bonding curve, it's gonna be safe for the design. So if I have a mechanical component made of this material, it's under this stress element, tau xy, sigma x, sigma y, tau xy. If I draw the Mohr circle for this state of stress, and I could find something like this. Something like this. So since this circle, which representing the state of stress for this one, is inside the bonding curve, we should be safe. So this is how this theory is working. So if I draw this and I could find something like this. Since some parts of this circle is out of the bond, we are going to have failure for that state of stress. So this is how this curve is working. Does it make sense? Now, what is this is the Mohr theory. This is the Mohr theory. But since it's difficult to find the bonding curve passing through these three circles, the simplified version of that is Coulomb-Mohr theory, which is working only on pure tensile and pure compression. So I get remove of middle one. I get remove of middle one. I end up to these two circles, the circle with the dashed lines. So ST, SC, these two. And what would be the bonding curve? It's going to be two lines passing through these two. Let me redraw this here. So this is ST, sorry, SYT or ST. The reason that the graph doesn't show Y because this theory is going to be applied for brittle material, and in brittle material we don't have yield strength, we have alternate strength. So it's representing ST. For brittle material is it should be SUT for and SUC. For ductile material is going to be SYT and SYC. So since I'm using for ductile material, I'm using SYT and SYC. So again, for a given state of stress, if the Mohr circle is inside these two lines, we should be safe. If it's outside of that, we have a failure. So now, for a state of stress, which is given a Mohr circle tangent to these two lines, something like this. Suppose you are given with a state of stress, you can find sigma 1, sigma 2, and sigma 3. You know how to do that. So you find sigma 1, sigma 2, sigma 3. So if I ask you to draw the 3 Mohr circle, it's going to be something like this. Sigma 1, sigma 2, if suppose sigma 3 is the negative. So if I ask you what would be the largest circle, the largest circle is going to be between sigma 1 and sigma 3. Now, if you pick the largest circle and draw it here, this one is going to be sigma 1, this one is going to be sigma 3. Now, if this circle is tangent to these two lines, this is sigma 3, this is sigma 1, this is SYT, and this is SYT. We can prove that. We can prove mathematically by looking at this graph. Sigma 1 over SYT or ST minus sigma 3 over SC, it's gonna be equal to 1. So sigma 1 divided by ST minus sigma 3 divided by SC, the summation of these two is gonna be 1. If the circle is tangent to these two lines. If it's not tangent to these two lines, if it's inside, the safe zone, we are going to have sigma 1 and sigma 3. This equation is going to change to this, sigma 1 divided by ST minus sigma 3 divided by SC equals to 1 over n, factor of safety. And this is a simplified type of the Mohr theory, or we call it DuctileMoher theory. For ductile material, we are using SYT and SYC. For brittle material, ST is S ultimate tensile, SC is ultimate for compressive. For ductile, ST is SYT, SC is SYC. So this is how you can define the DuctileMoher theory. Any questions so far? So, like as similar to these two, that we similar to this one that we worked on the three different cases. I'm gonna look at three different cases. One, sigma. We have plain stress element. Sigma A is greater than sigma B, and both are positive. If this is the case, sigma 1 is sigma A, sigma B is sigma 2, and sigma 3 is 0. So if I ask you to draw the failure theory based on the DuctileMoher theory or CMT, you need to find sigma 1, which is sigma A, divided by SYT, minus sigma 3 is 0, divided by SC is going to be 0, equals to 1. Then sigma 1 should be equals to SYT. So if this is SYT, sigma A should be equals to SYT. So any point here which has this specification, this line is going to be the failure theory. Any point on the right side is going to see the failure. Any point on the left side, it's going to be less than 1, so it's going to be safe. Case 2. Case 2. Sigma A is positive, but sigma B is negative. So sigma 1 is sigma A, sigma 3 is sigma B. So just plug in here. Sigma A dividing by SYT minus sigma B divided by SYC equals to 1. This is the failure. So if this is SYT, SYC should be different than SYC, and usually it's greater than SYT. So for that reason, this one is greater than this. So how can I represent this equation? It's gonna look like this. For case 2. If I want to draw this line, it's gonna look like this. And case 3, both are negative. So sigma 1 is 0, sigma 1 is 0. Sigma 3 is sigma B. Negative sigma B divided by SY C equals to 1, sigma B equals to negative SYC. This is sigma B equals to negative SYC. Due to the symmetry, I can complete the other 3 lines and end up to this safe zone. Which is gonna look like this. We have non-failure zone inside the box, and out of the box is gonna be the failure. It's very similar to maximum shear stress theory, except in maximum shear stress theory, this point and this point are the same, so you are gonna get a line and one square like this here, and another line with the angle of 45. But here, since we have different SYC and SYT, we are gonna see the different check. Alright, let me solve one example. there is a shaft under torque. (230 Newton-meter). So the shaft with diameter of 25 millimeter, made of aluminum with SYT equals to 160 megapascal and SYC equals to 170 megapascal. Find the factor of safety. So if there is a shaft, it's under pure torque, there is no other load presented there. So this is the only load. It's a ductile material, it's given that it's a ductile material. But since these two are not the same, we cannot use MSST and distortion energy. So we have to use this one. To find the factor of safety, we need to know what would be the sigma 1 and sigma 3. So first of all, I need to find the stress, all stresses applied to this. Since torque is the only load applied to that, shear stress is going to be T times C divided by J, or T times half of the diameter divided by pi e power 4 divided by 32, or 16T divided by pi e power 2. So shear stress is going to be 16 times 230 divided by pi, 25 millimeter. So it's going to be 75 times 10 power 6 Pascal, or 75 megapascal. So we have pure shear stress. For pure shear stress, if we draw the Mohr circle, is going to look like this. 75, negative 75. This is sigma A. This is sigma B. So sigma 1, 0, sigma 2, negative 75, sigma 3. So just plug in here. 75 megapascal. ST is the SYT is in the megapascal, so I don't change 75 to pascal. Divided by 160 minus sigma 3 is sigma B, which is negative 75. Negative 75 divided by 170 equals to 1 over n. Solve for n. 160 times 170 divided by 75 times 170 plus 160 times 75. It's gonna give the factor of safety, which is 1.1. So this is how this method is gonna work. I will post the homeworks by tomorrow. This is the next Thursday.